Hello learners, welcome you all to the session on scheduling queues and schedulers. The objective of our multiprogramming is to have some process running at all times to maximize our CPU utilization. The objective of time sharing is to switch the CPU among processes so frequently that users can interact with each program while it is running. To meet these objectives, Process Scheduler selects an available process that is possibly from a set of several available processes for program execution on the CPU. For a single processor system, there will never be more than one running process. If there are more processes, the rest will have to wait until the CPU is free and can be rescheduled. Categories of scheduling. There are two categories of scheduling. One is non-preemptive, the other one is preemptive scheduling. Non-preemptive, here the resources cannot be taken from a process until the process completes its execution. The switching of resources occur when the running process terminates and moves to a waiting state. A preemptive scheduling, here the OS allocates the resources to a process for a fixed amount of time. During resource allocation, the process switches from running state to ready state or from waiting state to ready state. This switching occurs as the CPU may give priority to other processes and replace the process with higher priority with the running process. Now let's see about a scheduling queues. As process enters the system, they are put into a job queue, which consists of all the process in the system. The processes that are residing in the main memory and are ready and waiting to execute are kept on a list called the ready queue. This queue is generally stored as a linked list. The following diagram shows the ready queue and various I/O device queues. A ready queue header contains a pointer to the first and final PCBs in the list. Each PCB includes a pointer field that points to the next PCB in the ready queue. The system also includes other queues. When a process is allocated the CPU, it executes for a while and eventually quits. It is interrupted or waits for the occurrence of a particular event, such as the completion of an IO request. Suppose if the process is making an IO request to a shared device, such as a disk. Since there are many processes in the system, the disk may be busy with the IO request of some other process. The process, therefore, may have to wait for the disk. The list of processes waiting for a particular IO device is called as a device queue. Each device has its own device queue. Now let's see about the representation of a process scheduling. A common representation of a process scheduling is a queuing diagram as represented as follows. Each rectangular box represents a queue. Two types of queues are present, the ready queue and a set of device queues. The circle represents the resources that serves the queue, and the arrow indicates the flow of process in the system. A new process is initially put into the ready queue and it waits there until it's selected for execution or it is dispatched. Once the process is allocated, the CPU is executing one of the several events could occur. The process could issue an IO request and then be placed in an IO queue, or the process could create a new child process and wait for the child termination, or the process could be removed forcibly from the CPU as a result of an interrupt and can be put back in the ready queue. In the first two cases, the process switches from the waiting state to the ready state and then puts it back in the ready queue. A process continues the cycle till it terminates, at which time it is removed from all queues and has its PCB and users deallocated. Next, we move on to schedulers. A process migrates among the various scheduling queues towards its lifetime. The operating system must select for scheduling purposes process from these queues in some fashion. The selection process is carried out by the appropriate scheduler. There are three different types of scheduler: a long-term scheduler, short-term scheduler, and a medium-term scheduler. Often in a batch system, more processes are permitted than can be executed immediately. These processes are spooled to a massive storage device, typically a disk, where they are kept for later execution. The long-term scheduler or job scheduler selects process from the spool and loads them into the memory for execution. The short-term scheduler or CPU scheduler selects from among the processes that are ready to execute and allocates the CPU to one of them. Let's see about long-term scheduler. This is called as a job scheduler, and the long-term scheduler decides which program must get into the job queue. From the job queue, the processor selects process and loads them into the memory for execution. Long-term scheduler runs less frequently. The primary aim of the job scheduler is to maintain a good degree of multiprogramming. An optimal degree of multiprogramming means that the average rate of process creation is equal to the average departure rate of process from the execution memory. Next, we'll see about short-term scheduler. This is also known as a CPU scheduler, and it runs very frequently. The primary aim of this scheduler is to enhance CPU performance and increase process execution rate. It is the change of ready state to running state of the process. CPU scheduler selects a process among the processes that are ready to execute and allocate CPU to one of them. The short-term scheduler must select a new process for the CPU frequently. A process can execute only for a few milliseconds before waiting for an IO request. Often, the short-term scheduler executes at least once every 100 milliseconds. In general, our most process can be described either as IO bound or a CPU bound. An IO bound is the one that spends more of its time doing IO than it spends doing its computations. And CPU bound, in contrast, it generates IO requests infrequently using more of its time during computations. It is important that the long-term scheduler select a good process mix of IO bound and CPU bound process. If all process are IO bound, the ready queue will almost always be empty. And the short-term scheduler will have a very little time to load. If all the process are CPU bound, the IO waiting queue will almost always be empty, devices will go unused, and again the system will be unbalanced. Hence, the system with the best performance will thus have a combination of CPU bound and IO bound process. Next, we'll see about a medium-term scheduler. Some operating systems, such as time-sharing system, may introduce an additional intermediate level of scheduling. This is known as a medium-term scheduler, and it is depicted in the following diagram. The key idea behind our medium-term scheduler is that it sometimes can be advantageous to remove a process from the memory and from the active potential for the CPU, and thus it reduces the degree of multiprogramming. The later, the process can be reintroduced into memory and its execution can be continued where it left off. This scheme is called a swapping. The process is swapped out and is later swapped in by the medium-term scheduler. And swapping may be necessary to improve the process mix or because a change in memory requirements has overcommitted available memory, requiring memory to be pulled up. Thus, in this session, we have seen about a process scheduling categories, scheduling queues, the representation of scheduling queues, and schedulers. Hope this session was helpful and thanks for watching.